That inspires them to ask questions yet to be asked. These programs, backed by the best available scientific expertise, are inspiring us all to behold the wonder of curiosity and understand the miracles of our astonishing universe. So please, open your eyes to science, because anything is possible. Science is the very basis of civilization as we know it. The study of science prepares young minds for a lifetime of learning and critical thinking. These are invaluable traits across business and industry and imperative for making.
Good evening, everybody, and welcome to our special event here at National Science Week 2017. My name's Tamara Davis. I'm a professor of astrophysics at the University of Queensland, and it's been my pleasure to be one of the conveners of this series that's been running this year on the dawn of the space age. And I'm going to be your MC for the evening. We'll soon welcome Professor Iver Cairns to talk about the excitement of the modern space age and Australia's role in it. Before we begin, however, I'd like to acknowledge and pay respect to the traditional owners of the land on which we meet, the Ngunnawal people of the Wiradjuri Nation. It's upon their ancestral lands that the Australian Academy of Science is built. As we share our knowledge, teaching and learning and research, may we also pay respect to the knowledge embedded forever within the Aboriginal custodianship of the country. I'd also like to thank our series sponsors for this evening's talk, Jura Wines at Geostation and Edge Catering. I hope some of you are enjoying some of their produce out the back there a moment ago. But for those who weren't able to have a glass of wine before we started here, welcome to those of us who are joining online. Tonight's talk is streaming online and will be available afterwards on the Academy YouTube channel. We love our online interactions, so for those in the audience who are on Twitter, feel free to tweet away using the hashtag #SpaceDawn, all one word, and @ScienceAcademy. Similarly, if you're watching online and you'd like to ask a question of tonight's speaker, we are going to take questions at the end. Then please use that hashtag so we pick up your question and we hopefully will be able to ask Eva a bit later. But with that, I would like to introduce tonight's speaker, Professor Iver Cairns. Professor Cairns completed his PhD at the University of Sydney in 1987 and then moved to the University of Iowa, where he spent a dozen years, until moving back to the University of Sydney, where he is now a professor. He is the past chair of the Australian Academy of Science's National Committee for Space Science, and he led the development of Australia's first Decadal Plan for Australian space science, which was published by the Australian Academy in 2010. Professor Cairns is taking major leadership roles in 2 spacecraft projects, INSPIRE and a subsequent CubeSat, INSPIRE-2, which is part of the European-led QB50 project. So tonight, Eva's going to tell us more about Australian satellites and where we can find them. I'm very excited to hear what he has to say. Please join me in welcoming Professor Iver Cairns.
Well, thank you very much for being here for this presentation. What I'd like to focus on is Australian-built satellites and where to find them. The focus is on, as you can see in this image, on an Australian viewpoint and on the development of capability for Australia as a whole. You can, of course, go overseas and buy a satellite to do various things. That's not really going to help Australia as a whole, unless you have some very specific data that you're interested in. We're going to focus instead on developing capability for Australia and arguing of the way in which it should be done. With these images, you can see all of the satellites that are currently in orbit around the Earth, plus some debris. And you should be thinking, is this what we should be interested in from the point of view of space? Is this a conventional satellite, or is it something new or different? And if this is the type of satellite that we should be building here in Australia for our purposes, why? Or put another way, is this the type of Australian space we should want? It's obviously beautiful. It's visionary in the sense, at least, that one can see to the horizon here. It's interesting. Look at these beautiful waves here, the way in which the wind has shaped the dunes. It's untrammeled, no human influence directly, at least. Is that what we want? Or something like this. Again, you might say, well, there's a road leading somewhere. We've got a far horizon. We have a vision. But is it a road to anywhere we want to go to? Does it have utility and value? At one level, of course, it's a road, so somebody at least thought it went somewhere. Useful, but there's nothing on it at the moment. If we are going to get into space as Australia, what do we want? And so coming back to this image here, which is, I should have said, from a website, Stuff in Space, by a young undergraduate student, James Yoder, in the United States. What sort of space history have we had in Australia, in particular for Australian-built satellites? What do we have now? What should we have? How soon should it be? Why? How do we, once we've decided what we really want, how do we get to that state? And what about the long term? And those are the types of questions that I hope to discuss with you today. In particular, a slightly expanded title is this one here, Australian-built satellites and where to find them, with the emphasis being on CubeSats and the QB50 project, which I'll come to. And the outline here, start off with the history and bring us into the present day. Then like to spend some time talking about why Australia should be in space, whether that's for commercial reasons or for public good reasons, as in research reasons, or should it be both? Talk about CubeSats, what they are. You've probably heard the word. Obviously, cube means something which is cubic shaped. Why would you want to have a satellite that looked like a cube? Why we should use CubeSats? Why we should do it now. Now actually turns out to be an absolutely fantastic time for Australian space research and Australian space industry, as I hope to convince you. And I'll then introduce you to the QB50 project, a European Union project, which I'm the leader of one of these spacecraft, INSPIRE-2, built here in Australia. But we'll also talk about UNSW ECO from the University of New South Wales in Sydney, and CubeSat, which is a University of South Australia and University of Adelaide project. And these are the first Australian satellites, Australian-built satellites, to be launched from the ISS, the International Space Station. They're our first satellites in 16 years. They are the fourth, fifth, and sixth Australian-built satellites that actually have gotten into space. And then I'll talk about the near-term developments for Australia in terms of using CubeSats, and why that's actually the way to go in building long-term value and a real space industry and space program that we should be proud of. So let's start with the history, and I was going to ask my audience here, have any Australian-built satellites reached space? Yes, some of you have been listening. Excellent. How many? 3. Interesting number. Okay. When? How recently? This is all Australian-built satellites rather than just perhaps the ones I might be connected to. Okay, I think a very precise answer. And regretfully for the rest of you, I'm going to go through it in a bit more detail. but hopefully that will be interesting. So our first one, as our colleague said, was 1967. It was launched, RESAT, standing for Weapons Research Establishment Satellite. It only lasted a short time, about 50 days, but it turned out to be, and this is really the shape of it, this is the RESAT, and it went onto the nose cone. It was the nose cone of a third stage of a rocket, Redstone rocket, which was given to us by the United States as part of a joint testing program with the British as well. And it led to Australia being the third nation to launch a satellite into space from its own territory. We were the seventh to have a satellite go into space, but the third from our own territory. This part was a loner, you might say, the US Redstone rocket, but RESAT was entirely Australian built and done extremely quickly. Basically, the Americans and I guess the Australians and the British did their experiments, found out they didn't need all of the 10 rockets that they had on hand at Wimmera, one left over. Said, what can we do with it? Well, it's too expensive to take it home. So instead they said, well, perhaps you Australians can use it, but you've got to do it quickly. We want to finish the program within 6 months to a year. Don't want to pay all these people to be in Australia. And so very quickly, people at the Weapons Research Establishment came up with this satellite. And at least at that time, and I think it's true today as well, the USA was very keen to share its capabilities for space and to help Australia to develop capability. Here's a bit more of a blow-up. I don't think you care about the details. I probably don't, being more of a theorist in many ways. But you can see many different components that had to be developed and put together really very quickly. It was pretty heavy, 45 kilos, but they had a Redstone rocket to launch it. This is something that Kerry Doherty, who some of you will know, gave me. Number 2 was a student-led project, an amateur radio satellite called Australis Oscar 5, and I actually know the expansion of this, and now I'm having a total mental blank on it. Let's see, this is orbital, this is amateur radio. I don't remember the other bits at the moment. But it was the 5th one, built by University of Melbourne students. You can see 3 of them here, but there were another couple. It's pretty heavy, about 18 kilos. Looks pretty simple, but not streamlined or particularly elegant. Had lots of pieces inside it. Took them roughly 1 year to build on a shoestring budget. 3 more to wait for the launch, and then it got into space and lasted for a reasonable time. And there's a very interesting website that some of you would like to look at, I suspect. It's got some history in it, some personal remarks, and really very interesting to see a team of approximately 5 people come together, work very hard on this, get to a significant place, some real achievements, and then go their separate ways. It's really quite interesting. Number 3 is FedSat, 2002. This was meant to be launched for the bicentennial. Sorry, it's not the bicentennial, it's the centennial, 100 years. And, but it was delayed. 60 centimeter cube satellite, relatively heavy. This is just a mock-up during the time that it was already in space. But this was our last spacecraft, Australian-built spacecraft, that got into space before the 3 CubeSats for QB50. And here we are today. This is from a little program called gPredict, which you can just download and look at any satellites, tracks, or orbits that you wish. Here we have the 3 Australian ones in a nice line, a string of pearls, as it's called, with UNSW ECO in front, INSPIRE, and then CubeSat. And these are AU01, so Australia 1, 2, and 3. And we'll talk about them a little bit more in the future. So let's come to this question. Why should we really care about space at all? And I'll give you 4 reasons. You may have a number of other ones, but I'm going to give you 4. And the first one is that it involves really fundamental blue sky science and research, both in terms of in technology as well. Here's an example that actually comes off the web very recently. It was in fact 2 days ago that there was a major story on this in the Daily Mail. But what we have is a view from the ISS, the International Space Station, of part of Mexico. You can see the curve of the Earth here, stars behind. This is a thunderstorm. You can see some of the lightning flashes which have been conglomerated together, so it's a time-lapse photograph. And then superposed on it here, you can see these little guys here. These are called sprites. And these are essentially lightning flashes that go from the tops of thunderstorms, so around about 10 kilometers of altitude, where your jet planes fly, up into space. Only discovered about 20, 30 years ago, still not understood, and yet it involves lots of interesting plasma physics. It involves our world and the connection between the atmosphere and space. Here's a blow-up of it here. Just some other numbers that might excite you. 100 kiloamps of current. Orders of magnitude, obviously more than in our current standard power supplies. The red's due to excitation of nitrogen lines, and it's due to fast electrons being accelerated down here by essentially double layers, electric double layers, accelerated up into space, and some of them down as well. And then they hit the nitrogen and excite the spectral lines. So just blue sky, fundamental science. Very interesting, very close to Earth. And it's just looking, it's an example of looking at the world around us and trying to understand it. Another one is space weather. What's space weather? Well, it's a bit of a buzzword or a buzz phrase. It's a broad term. It means the conditions in space that may affect human systems and activities on Earth and in space. It includes the other area called space situational awareness, for those of you who are experts. And I'm not going to dwell on that. But most of these are driven by solar activity, by so-called coronal mass ejections, which I'll show you a video of in just a moment. And I'll give you some commercial reasons why you should be interested. But here's one from a very big player, the United States, President Obama, just about 6 months, I guess it's a little longer, 8 months ago now. He actually put together an executive order about space weather events, and preparing, rather, the United States for it. Why? Because these space weather events can significantly degrade critical infrastructure, simultaneously affect health and safety across the continent of the United States and elsewhere. And it's an all-of-nation endeavor. It's not just something that you care about in the state of Iowa, for instance. These are things which can give rise to major damage and a change in the ability of humankind to survive. Let me explain that in a little bit more. But first, I'll show you a video, or rather a video, but of a simulation of a space weather event. What we're going to see is a large flare on the sun with a coronal mass ejection, which is just mass leaving the sun. We'll start to see it forming over here in a moment. It'll come towards the Earth. So here's our flare, coronal mass ejection, then leaving. We're going to see the Earth and its magnetic field lines in a moment. See the field lines here of the dipole. We're going to get a process called magnetic reconnection occurring here and here. Lots of detailed plasma physics. But then energetic plasma raining down onto the Earth, over the polar cap, over the auroral zone, giving rise to changes in the magnetic field, large electric fields, which along, for instance, power lines can give you large voltages and currents. Those then destroy transformers and destroy entire electrical power grids. And there's a few examples like this over the last roughly 100 years. The biggest one to think about is the Carrington event of 1859, when the auroras, instead of being up at 60 degrees magnetic latitude, so down below Tasmania towards the pole, or up in the United States, in Norway, up above Washington, D.C., for instance, in the United States. But auroras down almost to the equator. You had fires starting by arcing from telegraph wires, which were the equivalent then of electrical power grid wires, because you've got these large changes in the magnetic field, large electric fields, large voltages on telegraph wires, and then breakdown of the air and creation of lightning, effectively. It's predicted today that if that event occurred, it could have taken out the United States East Coast power system for up to 10 years. The associated costs are roughly 1 to 10 trillion American dollars for up to 10 years. And an Iraq war is costed round about $1 trillion. So these are catastrophic events. Can you imagine living in Washington, D.C. or various parts of the United States without electrical power? How will you keep your food? How will you keep cool or warm, as the case might be? Really could be catastrophic for modern humankind that relies upon electricity for almost everything we do. And yet, only about 4 years ago, Earth actually missed a Carrington-sized event by 1 week, because the sun had rotated 90 degrees and it blasted off 90 degrees away from the Earth-Sun line. Here's another example, which I won't go into. So what about another reason? One of them is just public good and national security applications using Earth observations and GNSS and GPS data. Huge numbers of these, sure to increase in value, in number, and value for that matter. Two basic techniques. One is just imaging, various spectral lines, and one is GPS, and I'll go only over the first one. We're all familiar with the idea that satellites can look down and see what's on the surface of the Earth or in the atmosphere along various tracks, see whether we've got wheat, for instance, and how healthy the wheat is, whether we have forest, things like that, whether we have a forest fire in a given region. These are really important for working out whether we've got significant hazards at a given time that we need to address. And of course, issues like, do we have a smuggler's boat approaching the coast of, let's say, Australia or not? That's probably not anymore. Anyway. Okay, another one, just commercial applications. Here, we've really gone over this one already. It's using Earth observations data or GNSS data to do something commercial. For instance, predict whether or not there'll be enough water for a given town. Or looking at the current state of the wheat in, let's say, Eastern Australia. Are we going to have a bumper harvest in Australia? Will we be able to sell it to, for instance, the Russians or the Chinese at a good price or not, compared with what their harvest is doing? Another one is just that the GPS data are used to time essentially all financial transactions today. If you don't have your GPS data, stock exchange goes down, etc., etc. There's, of course, the Internet of Things and communications, which you can use space assets for. Many of these areas are high growth startups, like Planet Labs, which in 2015, whose chief technical officer, Chris Boschhausen, is former chief technical officer, Chris Boschhausen, is Australian. They got $180 million in venture capital funding just about 2 years ago. So obviously high value. You've got others like Sabre Astronautics, Fleet and Neumann Space, which this year got $5 million in Australian and overseas venture capital. There are about 30 or so of these startups today. So obviously a commercially active and interesting area to be in. But maybe a bigger reason is the one given below, which just is the huge potential for Australia to improve its economy and to provide useful devices for people across the world. So, for instance, improving Australia's GDP by $1 billion per annum, if only 10% of our annual spend on space was brought home. That's using an economic multiplier of 5. You know, $1 billion is a sizable amount of money. Looking at some of these regions or these areas like the small satellite market, it's forecast to grow at 23% per annum. Huge growth rate. Same is true for essentially all space industries. Much faster than most conventional markets or industries on Earth. So a lot of potential here. And then look at the United Kingdom, which has been very slow to get a national space policy and to get a space agency. They are aiming at gaining a total of 10% of the global space market, which is about $1 trillion a year, of that amount by 2030, by investing around about 0.5 billion per annum. So they're looking at making significant amounts of money via these commercial applications of space data and space assets. Australia should be aiming at something more like 1% perhaps, because we're starting off as new kids on the block, but that's the sort of thing we should be aiming at. Major reason why we should be in space is the commercial applications. So what about CubeSats? What are they? Well, they're basically cubes, as you might hope. 10 centimeters on a size, all of them made up of cubes of 10 centimeters on a size. You can stack them in a 2-unit one by putting one on top of the other to make a total length of 20, a 3-unit one, etc. More complicated ones. Low mass, about 1.3 kilos or less per unit. It's an old idea in some sense, dating back to '99, so it's roughly 20 years old. But it has some really strong rationales. And the primary one is the one I've given here, is that it allows the scientists or the commercial people, or at least the non-engineers, to focus on what's interesting to them, the reasons why they want to do a set of measurements, not on the engineering of the satellite itself. So you focus on what's interesting to you, and you regard the CubeSat or the satellite as a tool, not as the raison d'etre. In other words, it's not just making a toy for the boys and girls, it's making something that has real use. And the purpose of it is not to just excite the boys and girls who are making it. Why does it work? Well, it's basically because you've set a standard for design. It means you don't have to decide whether your satellite should be, for instance, 23.351 centimeters in one dimension and 74 in the other one, etc., etc. You say, no, everything's in units of 10 centimeters. It allows you to design much more easily, reduces your errors, reduces your uncertainty. It's standardizing, not going to everything being bespoke. That then leads to commercial off-the-shelf systems that you can buy relatively easily, proves the reliability, reduces the cost. And a point here is, do any of us really want to design our own fridge or build it? No, we buy it, because it doesn't interest us to build it, most of us. Let's focus on what we're interested in and what we want to do with the data. So we've got these two reasons we've already given. It's also easier to build, integrate and test, reduce time, so you can go from concept to market, which might mean in this case launch and then a commercial application in much less time. Let's say 1 year instead of 10 years like most NASA or ESA projects. We can use piggyback launches and standard deployers, much less expensive. We don't need expensive facilities. We just need a room that's clean, not a clean room. Costs are orders of magnitude less. So focus on what interests you and not on the satellite details. So why now for Australia? And what does this mean for a national space program, for instance? Well, for instance, INSPIRE-2, which we'll come to in a moment, 10 months from start to delivery, including the design, less than $150,000 of cash spent, no federal funds, and most of those funds were used for the commercial off-the-shelf parts, and then for launch, the testing and the travel. So very, very cost effective, and yet we're going to do some fundamental science. In fact, all 3 Australian QB50 satellites, less than $500,000 each. Put in perspective, $500,000 is about the cost of a Boost Juice franchise. So if you're a small business person, why not design a spacecraft or a project that involves space and go into it? These also demonstrate breaking the economic barrier that many people have pointed to for Australia to enter the global space industry. Now the costs are, $1 million or so. They're not the cost of a standard 1 meter on a side spacecraft, which is $10 million. It's not $1 billion for all that facilities. It's a few million, perhaps. This is the way to do it. They also demonstrate Australian space capability. We've got indigenous state-of-the-art capabilities, which we can use to develop space industry. There are similarities with UAVs, or uncrewed aerial vehicles, as I'll call them. So we can take a device that you've developed for CubeSat and use it on a UAV, or vice versa. There are many good reasons for doing that. And they're a stepping stone to larger satellites. So if you hate CubeSats and you want something big, well, learn to do the CubeSat and then take the lessons learned and apply it to a bigger satellite. So what about QB50? QB50 is a pun. It's meant to be cube and 50. So 50 CubeSats is what it was meant to be. It's a European Union project. Turns out to be really QB36, because we actually have only 28 that were launched from the International Space Station, another 8 which are launched from an Indian launch vehicle, 36 of them. And what are they going to do? They're going to look at this domain here from roughly about 400 kilometers, 450. This is an old slide, the space shuttle, the International Space Station's here, about 400 kilometers. We're going to be looking at this domain from here, so the edge of space, so the edge of the thermosphere and the ionosphere, sorry, not the edge of the ionosphere, but part of the ionosphere, down to about 80, 90 kilometers. And in connection with that, well, the aurora is in this region here, above 100 kilometers. The ionosphere really starts here. This is the region where you see meteors. The ozone layer is here. So we're going to be looking in this region here, the so-called ignorosphere. Because it's really difficult to get data unless you do it from the ground. Because a satellite, if you put it in at 100 kilometers, it lasts less than a month before it comes down. If you just send up a rocket, it goes up there and it's down again within something like 5 minutes, 10 minutes. You get maybe a minute's worth of data, maybe 2 or 3, not much. So what we're going to do is try and probe the ignorosphere, so the ionosphere and the thermosphere. We're interested in the strength and the composition and the variability of the lower thermosphere and the ionosphere. And yet, these 3 are Australia's first CubeSats. They're the first satellites that we've launched from the International Space Station, only our 4th, 5th, and 6th satellites, and our first in 15 years. And here they are, displayed in Wombat XL at the Advanced Instrumentation Technology Center at ANU up on Mount Stromlo. So you can see here the edge of here's the back end of that vacuum chamber, Wombat XL. Here's UNSW ECO. My one here is INSPIRE-2 at the back with its little antennas deployed. And here we have CubeSat. This is roughly 20 centimeters. This is exactly 20.0 centimeters tall, 10.0 centimeters across, all 3 of them. So here they are. That's what they look like. They look black because of the solar cells that you're looking at, primarily. And so here's a little bit more detail about CubeSat. So their objectives were to design, build, test, and deliver one, build a team, develop some indigenous subsystems, so in particular the attitude control, which direction is the spacecraft pointing, what would you be able to observe on the ground at a given time, communications, and various other things. Matt Tetlow is the leader, and here you can see some of the CubeSat taking shape here, and if you took off the outer skin, you might say, or the outer the sides, and look inside, you see these individual boards that are 10 centimeters on a side and go in, and they have all the electronic components on top of them. Here's some of these pushed into here. So that's CubeSat, UNSW ECO. 3 UNSW payloads and 1 from the QB50 project. Pretty small amount of money, about $250,000. 30+ students involved in working on it. And here is one of them, that's Tom Croston. Jun Wen Chung is the main engineer, and Elias Abutanios is the leader of that. And this is Mike Petkovich from AITC with Wombat behind it. And I forgot to say that CubeSat involved over 100 students, undergraduate students, and then a small team on top. I'm going to spend a bit more time on INSPIRE-2, which is, you can see here the names of the team, one of whom is in the audience here, I guess apart from myself, that's Rod Foswell. Roughly 20, in fact 2, David Dahl as well. It's a 3-university project that started on the 1st of October in 2015 and then was delivered in August of 2016. University of Sydney, ANU and UNSW. Here's the spacecraft itself. You can see the solar cells. This is various antennas here. And then this is a GPS antenna for a UNSW instrument inside it. We have a number of students involved, and then you see here some pictures of various people, quite a diverse group. Christine Charles is the second in command, Andrew Dempster is the third from UNSW and ANU. Rod's here, David Dahl was here, Xiaofeng Wu. Jiro Funamoto did lots of the actual building. So lots of payloads, 3 from the University of Sydney, 1 from QB50. UNSW did most of the engineering work, but also provided an instrument, and then ANU provided the commercial off-the-shelf parts and the main ground station. You don't care about those details. What you probably want to see is pictures of some of the things we built. So here's Jiro and Wayne Peacock with a microdosimeter over here, so measuring energetic particles, and similarly here a energetic particle instrument, basically just a Geiger counter that we built, and here's an electronics board as well. So these are the types of things you build, relatively simple, commercial off-the-shelf parts that come in nice boxes, that you can then put together with great difficulty. Even though they're meant to be plug and play, they're usually not. Some of you will remember that used to be the claim for laptops and PCs, etc. Now they pretty much are plug and play. In the future, the commercial off-the-shelf parts will be much more that way, and that's one of the directions in which we're trying to progress ourselves at the Universities of Sydney and New South Wales. Here's an example of a room that's clean, that we put the spacecraft together in. You can see it's cluttered, not too much light. There's certainly no clean room. From a formal point of view, it's being put together in a room that's clean. Here's some of the individual PCBs or boards that are being put together and stacked. Here's the frame that we bought, for instance, putting them in. Lots of detailed work. Lots of it involving students, but also people who are a little bit older, such as me. Here we are, essentially in the flight configuration. Here we are in the thermal vacuum chamber, having deployed the antennas. I wanted to show you some of the first data from INSPIRE-2. This is spacecraft health data. It's not the scientific data, unfortunately. But what we have is the battery voltage from about 8.15 to 8.35 volts. You've got the charging current here going into the battery, the discharge current going out in red. Let's ignore this. And you've got temperatures. What you might want to do is just say, well, what might I expect of a spacecraft that goes into local night, so it's eclipsed by the Earth? Well, there'll be no solar sunlight, of course, not reaching it. So we'd expect the charging current to go down. We'd also expect it to start getting cold because it's no longer got sunlight on it. And if you look over here, you see the temperature starting to go down once we go into local night. Come back out, and it starts coming back up again. and the battery voltage goes down here just because we now have drains on the battery, such as the output currents into the various spacecraft systems, which is not being matched by current coming from the solar cells. Okay, so that's where we are at the moment. What about the future? I'll talk a little bit about a training center for CubeSats, UAVs, and applications that was funded this year, but hasn't yet formally started. Talk about an expert review of Australia's space industry capabilities that Minister Synadinos announced recently. So this is a training center that Andrew Dempster and I and Eleanor Bruce are the primary leaders of. Its basic intention is to develop a world-class Australian space industry based on CubeSats, UAVs, and related products. We're focused on human capital, so training students and postdoctoral fellows, fundamentally changing the capabilities of CubeSats, UAVs, and instruments, and progressing those devices to create major commercial value. So actually trying to bring some of that $2 to $4 billion spend that Australia has back home and to provide and really develop industries. We have something like $6 million over 5 years, and we're going to launch one CubeSat each year and have one long UAV campaign per year. Here are the partners. There's 5 corporations, 4 universities, 2 American, Rochester and Texas A&M, and we have 4 government units as well. So the Bureau of Meteorology, DSTG, so Department of Defense. And somewhere here, I should have one other one. Oh, the Australian Astronomical Observatory. Recently, there's been an announcement about a review of space industry capability. Then you might have heard statements about how this related to a space agency. If you look carefully, the minister's remarks are all about an expert review of capabilities, space industry capabilities. There's nothing specifically on creating a space agency. And it's important to just make these points here, I think, that there's no significant international space agency that focuses only on space industry. Think of NASA, ESA, JAXA, the British, etc. What you've heard about them doing is almost always their public good research that they've done. For instance, Juno going to Jupiter just recently, or Solar Probe launching soon to go to the Sun. You hear about that rather than about the 50% of their budget that they spend on space industry development. And Australia really shouldn't be any different. So space industry is vital. I'm totally committed to that with my training center, for instance, but it's not the only game in town. Lots of other things we could talk about, the BRI CubeSats and these startups here, but we don't have time. I think the point is it's exciting. We've got now with CubeSats a real capability to create an Australian space effort that is significant worldwide, that does provide major commercial value for the nation and products that we need, but also does public good science and research that excites people, makes them want to go into science and engineering or mathematics, which then leads them into accounting or wherever else. We've got to have that educational pool. Can't rely upon people being excited about making gadget X. Most people, when they're 10 years old, 15 years old, 20 years old, they're not focused on that. They're focused on bigger picture things. CubeSats are a really great way to go. They're standardized, powerful, flexible, low risk, and cost effective. Allows you to focus on your goals and interests, not on the engineering. I'd argue that we've demonstrated that we've broken the economic barrier to Australia entering the global space industry by flying our 3 CubeSats. And it's also shown that we actually have significant space capability. It's an exciting opportunity now, but we've got to make sure that we balance the public good research with the space industry and national goals. Thank you very much.
Thanks very much, Eva. That was fantastic. I think you've given us a powerful argument for why we should send more Australian tech into space, and not only that it's a useful thing to do, but also very possible. It's now time to open the floor to the audience for questions. I'm sure you've sparked some curiosity amongst here. We have a few microphone runners here and also a microphone in the centre at the top. So I believe the first question's from over here.
I'm wondering if you could tell me how they maintain attitude control on such a small device.
So basically, you're going to use the Earth's magnetic field, and you put currents into coils to create magnetic fields on the spacecraft itself, exert a torque then, and you can then reorient the spacecraft using your own attitude determination and control system. So you're basically just running a current, create a magnetic field, and then a torque.
Extremely clever.
It's actually something that was first flown by it's Oscar 5. So the Melbourne students that I mentioned earlier, they were the first ones in the world to do that.
That's really cool. I did have a quick Google while you were up here. Oscar is orbiting satellite carrying amateur radio.
Excellent, thank you.
Not a particularly inspiring middle two words, but there we go.
The main anchor station for these, whereabouts is it located?
What do you mean by anchor station?
So how do you actually control the satellites?
So for us, for INSPIRE-2, we have a ground station here at ANU that Christine and Rod and Dimitris Tesifoukis run. Then we have one at UNSW as well. And so it's really a very small system. It's basically it looks like a television antenna, a Yagi antenna, and you just point it, but you've got to track the spacecraft, and then you've got a relatively simple set of devices to encode the information.
On the UAV side, are there any particularly exciting projects in that field?
That I can talk about? Well, as you know, I suspect, the Defence Department's very interested in UAVs, as are pizza delivery. Oh, sorry, UAV is an uncrewed or unmanned, if you're more old-fashioned, aerial vehicle. Yes, you even heard of people like pizza delivery groups trying to use UAVs as well. I guess the term they don't like is drone. But a UAV. Sorry, your question again was, oh yes, particularly exciting things. So basically anything that you can do from space, you might want to do from a UAV as well. And the reason is that if you're on a UAV at, let's say, 2 kilometers altitude, or let's say up to 10 if you're really want a challenge, then you have a much better spatial resolution for, let's say, an imaging camera. Your individual pixels are much smaller. They might be much less than a meter in size. But up in space, they might be 2 meters in size, or 5 or 10 if it's, or even larger. So the combination is actually powerful. And so we particularly want to fly the same instrument on a UAV and on our CubeSats, so as to be able to use the CubeSat to look at the large scale view, so the macro picture of, let's say, of whether there's an iron ore body on the surface in this part of Australia versus that part, and then we use the UAV to go in and focus in detail on it. But otherwise, most of the spacecraft systems we're interested in will fly on both, and will sell to both, hopefully.
How are kids like me from public schools involved in this? How can we be involved in this?
So how in various ways. One is just learning enough science and mathematics to be able to be able to look at, for instance, some data, interpret it. You might also be in a school that has decides to build a small CubeSat or a UAV. You can buy many of the pieces commercially, so off the shelf, put them together, learn coding, for instance, or computer programming to be able to get the bits to talk to each other, then fly it on a balloon, for instance, or on a UAV, and then perhaps be part of a student project in a competition that has an idea that we at our centre or someone else will say, that's wonderful, let's go and do a collaboration with this school.
That sounds like it's one of the really exciting things, that it makes launching things into space accessible to many different people. I liked your analogy with the sort of a Boost Juice franchise. If you wanted to make a space mission, you could do it for that amount of money. Next questions? There's one right over here. Next one up.
First comment is there was a report in the last day or two about students from a Western Sydney school put some, just launched just today or yesterday, some satellites which were going up to the space station. I don't know any details further than that, so that's relevant to your last question. The other thing, you sort of seem to skirt over what these satellites actually do, unless I was asleep when you mentioned it. Can you give us some examples of what use they are? Thanks very much.
Right, so what will they use? So do I have access to any of this?
Yes, we're getting signaled yes. 1 second.
Okay, so I'll be old-fashioned to just do this all the way through, hopefully. Maybe not. So if you can go to the two white slides, blank slides, and then we'll go from there. Okay, there. Okay, so, whoops, don't want that one. Somewhere here. So these are ones, okay. So for instance, we're going to look at the strength of the ionosphere. What do I mean by strength? I mean the number of electrons per unit volume. Why do we care about that? For instance, radio waves at suitable frequencies, below about 30 megahertz. So it's either the AM or FM, and I always get it confused, which it is. But your standard radio stations, they send radio signal up and then reflect off the ionosphere and come back down, for instance. We're going to be able to look at that directly, and in particular look at the changes of the strength of the ionosphere as a function of time and position. So here's, some of you will have seen the media event, which was Cleo Loy's Plasma Tubes in the Sky YouTube video. If you haven't, look up Cleo Loy and Plasma Tubes in the Sky on YouTube and watch it. And this is a still of it. Basically shows regions of higher and lower density arranged in the sky. And you can see that they're aligned along these white lines, which turn out to be the magnetic field lines of Earth. And this is a structure, a tube in the sky going from the North Pole to the South Pole. No one knows why they're there, in detail at least. We're going to be able to send little INSPIRE-2 across it like this, measure at the same time as people look at radio data. So this is actually from the Murchison Wide Field Array, and they look at the movement back and forth of radio galaxies, and from that they work out what the densities are. We'll be able to compare the two of them. So we're going to be looking at the strength of the ionosphere as a function of position and time, day-night changes, space weather events, the eclipse that's coming up in just a few days. That's going to leave beautiful patterns in the ionosphere as a function of time, which will evolve in various ways we don't understand properly. And if our instrument is turned on at that time, which it is not yet, then we would hope to look for that. So it's that sort of data.
Great. I think we had a question down here, then one up the top there, and then another from over here, hopefully, if we have time.
Eva, thank you for that wonderful talk and explaining how the technical and economic barriers have been breached. I think there was a role of Australian government in this as well, and I believe the QB50 partners from Australia also made some important progress on some of the regulatory issues surrounding getting satellites into space. Would you be able to say a few words about that?
Yes, so we're actually extremely grateful to Minister Hunt and Minister Pine and Minister Synodinos for their efforts in waiving the insurance costs and the liability aspects of the 1998 Space Activities Act. Those words will not mean much to you, but the issue is that under the Outer Space Treaty, which is Australia is a signatory to, the launching state, which is Australia in this case, if it's our satellite, is liable to for the costs if there is a problem, damage, either in space, but especially on the launch. And it's really expensive to insure. The sort of minimum allowable estimate of the cost is roughly $30 million. And they usually say, well, the insurance, well, it's, let's say 5 to 10%. So you're looking at $1.5 to $3 million just to be able to buy the insurance. And as you can imagine, the University of Sydney, when I went along and talked to them about this, they said, ha, 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 you must be kidding. You're not going to get $1.5 to $3 million out of us for just, insurance, especially when your spacecraft is costing, let's say, $150,000. So the ministers were able to use their power to waive those insurance requirements. And we're very grateful. And now it seems as though with the ongoing review of that act, that will be a standard exception for public good small satellites.
Great. We're running out of time, but let's get these two questions if we can. In the back.
Thank you. On your first slide, you showed an image of all the satellites around the globe. At what point does the volume up there start to cause a problem?
Sorry, can you say the last part again?
The volume up there, volume of stuff up there cause a problem? Cascades.
So, yes, so space junk. Well, I guess the way I'd put it is that I don't think you've heard of any geosynchronous satellite hitting another one or going offline because of collisions. So even though a geosynchronous satellite might be, 2 meters on a side, so, basically as big as I am, but a little bit more spherical, it's a tiny, tiny, tiny fraction of the available volume for that spacecraft to fit in. So I think the issue is that, so it's very rare for something to occur that far out because the volume's very large. Closer to Earth, when you're up at 400 kilometers, 1,000 kilometers, sort of distances like that, then the available volume's much smaller, so it's going to be much more likely for a collision to occur. And so that's where the space junk is really a major problem. And I think many people would say we're not at that point yet, but within 5 years, we might be in a situation of difficulty with regard to space junk.
Okay, and so our final question of the evening.
It's actually a double question. What's the life of these satellites before they deorbit because they burn up? And secondly, is there any debris in launching all these CubeSats, or are they a clean launch?
Okay, so the first question, the lifetime for our QB50 ones, it's around about 12 months to 15 months because we were pushed out of the space station at roughly 400 kilometers altitude. Now, if you go down to 300 kilometers, then your lifetime is of order 1 month. So it varies significantly depending on your altitude. Let's see, the second one was, sorry.
Do CubeSats leave any debris when they're launched, or are they a clean launch?
No, they're a very clean launch because the way in which it's done is the CubeSats get put into a pod, in our case for the company NanoRacks. So it's basically 3 satellites end to end with some sides and a door at one end, and at the other door you've got a spring. And so they open the door, and then the spring, which is compressed, goes ping, and the spacecraft gets pushed out at a pretty low speed, about 2 meters a second or so. So that way of doing it doesn't create any debris, or at least none beyond, a few dust particles that might have been in there with the CubeSat. So really very, very clean. It's simple, elegant, works almost always. And if you want to, you can go onto our website, for instance, and look at our deployment video.
That sounds exciting, like it's sort of like a jack-in-the-box sort of satellite coming out.
It's exactly like it. It's
really
horrifying.
good visuals that I have from now.
It's horrifying because you look at it and you see the 3 satellites, and so you expect one to be in front of the other one. But it turns out that because of the connectors they put between, they often just have 2 or 3 connectors rather than 4 under each corner. And so the spacecraft, when the spring operates, it goes and compresses some of the connectors more than others, and so they actually start toppling as they come out. And I saw that for ours, and just at the time that it looked as though 2 of them were hitting each other, there was a noise on the microphone that the astronauts made that went clunk. Of course, you look at that and you say, oh, and then you say, but sound doesn't travel in space. So you realize that it was just a chance thing.
Well, on that note, thank you very, very much for your talk today, Iver. Let's give him a round of applause. I certainly found that very interesting, and thank you to all of you for joining us here tonight. The talk will be available on the Academy's YouTube channel shortly. I hope you all enjoyed tonight. I'm really appreciative of the Academy for hosting events like this, whose aim is to increase the public awareness and understanding of science. You may know that the Academy's activities also include programs that engage school students, such as their Primary Connections and Science by Doing programs, the new maths program Resolve, and their wonderful Science Explainer website, nova.org.au. Now, the Academy is a not-for-profit organisation, so thank you for everybody who has supported us by purchasing your tickets for tonight's event. Your contributions help continue to bring speakers and important topics to a broader audience. If you'd like to explore other ways to support the work of the Academy or make a donation, you can visit the Support Us pages on the website. One last thank you to our sponsors for this evening's talks, Jura Wines at Geostation and Edge Catering. And thank you once again. Enjoy the rest of National Science Week 2017. Good night. Thank you.
Form choices about critical issues facing society. Issues such as climate change, immunisation, food and water security. The Australian Academy of Science, this fellowship of the nation's most distinguished scientists and mathematicians, is introducing young minds to the joy of science through inspired teaching and learning that will set some children on the path to a career that inspires them to ask questions yet to be asked. These programs, backed by the best available scientific expertise, are inspiring us all to behold the wonder of curiosity and understand the miracles of our astonishing universe. So please, open your eyes to science, because anything is possible.